Hello, Mr. Patterson here, and in this video we're going to take a look at changing state and heating curves for a substance. All right, for a moment here, let's consider water. All right, that's going to be the substance in question. We're going to go from a solid to a gas by heating that material. So we're going to take a look at this simulation, and what it shows us is we have solid ice, and in a container we're going to add some heat to it. We're going to monitor temperature as time goes on here. Also, in the animation, you can see the water molecules locked in position in the ice there. You notice they're arranged in a hexagonal pattern, but they are vibrating. All right, so that shows that they do have some temperature. They're moving around here. Okay, so let's add heat to this and see what happens. So you notice the temperature is going up, and then we start to change state. We're melting. Now the particles have freed themselves up. They're moving around, sliding past each other. And all the solid is gone. Now we have a liquid. And the temperature is increasing again. You can see the particles start to speed up as the temperature becomes higher and higher. Every now and then a particle will leave the container. So we're approaching the boiling point of water, which is 100 degrees Celsius. So we're going to change state again. So right here now we're starting to vaporize. Particles are leaving the container at a very high rate. The temperature is remaining constant. It's 100 degrees Celsius. All right, now all the water has left the container. It's all been converted to gas. Now the temperature is increasing again. All right, so what's going on here? Okay, why does that graph on the left-hand side of temperature versus heat look the way that it does? And it all comes back to intermolecular forces. All right, so let's take a look at a heating curve and explain what's going on. All right, so here's another heating curve, very similar to what we just saw, where we're taking water and we're going to heat it up from a solid and we're going to turn it all into a gas. On the x-axis, you have the heat that is absorbed by the material, and on the y-axis, you have temperature graphed here. Okay, so let's look at the different parts of the graph. You'll notice there are a few sections here that look very similar. All right, so 3 sections here. What we're doing is we're changing temperature here. So the particles are going from slow motion, slow movements to faster and faster, larger movements. Okay, and that goes back to our definition of temperature. Temperature measures average kinetic energy. The higher the kinetic energy of a particle, the faster that it's moving. Now let's consider these 2 areas on the graph. Notice that they are flat. All right, so what's going on here? These are changes of state. Changes of state. All right, so we're melting in the first one, and then we're boiling in the second one. So why does the temperature not change there? Well, let's think about that for a second. That would mean that the particles are not changing their kinetic energy. They're not speeding up. But we're adding energy to them. They should speed up. What we're doing is overcoming intermolecular forces. It requires some amount of energy to change state. We got to spread those particles out farther and farther. Okay? In the case of melting, what we're doing is we're overcoming the fixed positions. Those particles are locked in fixed positions. We overcome the intermolecular forces that hold those particles in fixed positions so that they can slide past each other and turn into what we call a liquid. In the event of boiling, what we are doing is we're spreading the particles out really, really far. So we have to apply a force for a long enough time over such a large distance so that we essentially separate the particles out so they are no attractions or very, very minimal attractions between the particles. And that takes quite a bit of energy. All right, how much energy? We'll take a look at that here in just a moment. First, we need to define a couple things. We need to talk about what's specific heat and latent heat. All right, specific heat, it's the energy required to increase the temperature of a certain amount of material. Okay, so energy to increase temp. Now, we can only do this when we're not changing state. All right, and this specific heat is measured in joules per gram degree Celsius. So it is a description of how much energy per gram per degree Celsius is required to change the temperature. All right, latent heat, on the other hand, is the amount of energy to change state. Okay, since the temperature doesn't change, we have to look at something else. It's listed, okay, it is a description of how much energy in joules it takes per gram of substance just to overcome the intermolecular forces. Okay, so how are we going to calculate these? Specific heat. And we need to define one more thing. Q, this is heat. All right, Q is going to represent heat. So we have two ways of finding that. If we're in one state of matter and we're increasing temperature, what we're going to do is we're going to take the mass of the substance times its specific heat times the change in temperature. Okay? And for a state change, we're going to find Q, the heat required, the energy required, by taking the mass of the substance times the latent heat. And there are different types of latent heat. Latent heat's a fusion or vaporization, and it depends on what state of matter or state change we're going through. All right, so let's go back to our graph and take a look at where these apply and do a sample calculation. All right, so here's our graph, and I'm going to zoom in and move around here, so try to bear with me. All right, so let's look at this first section of our graph where we have a solid present. Okay, so we can see that the temperature is changing. So for this area right here, what we're going to do is use this, Q equals MC delta T. All right, and that specific heat that we'll use for this is a specific heat of ice. All right, this section here, what we're going to do is find the amount of energy required to make that change of state by taking the mass of the substance, the mass of the water in this case, times the latent heat of, and it's going to be labeled fusion. All right, latent heat of fusion is the amount of energy required to melt, or the amount of energy given off when you freeze. All right. For this segment here, we're changing temperature again, so it's MC delta T. This segment right here, we're changing state again, so it's going to be the latent heat. This time it's vaporization. This is the amount of energy required to change state from while we're boiling, or it's the amount of energy that's given off when a substance is condensing. And then the last segment right here, we've got a gas, it's changing temperature. It's going to be Q equals MC delta T. Now, once again, let me remind you that specific heat, the C in all of these three right here, all have different values because they are different states of matter. They have specific heats that are just that, specific to that state of matter. Okay, so let's assume that we're going to take 100 grams of H2O from what did we start out here? -40 degrees Celsius to And the graph looks like, let's call it 140 degrees Celsius. So we got to go through all of these 5 different segments here. Okay, so let's set those equations up and find out how much energy it requires to take 100 grams of water from negative 40 degrees Celsius to 140 degrees Celsius. All right, so I'm going to demonstrate the first two segments of the graph, how to calculate those energy requirements, and then we'll jump through the rest really quickly. All right, so the amount of energy needed to raise the temperature from negative 40 degrees to 0 degrees. So it's going to be 100 grams of water, or ice in this case. Our specific heat for ice, and you can look this up in your textbook, or it'll be given to you in a problem, is 2.05 joules per gram degree Celsius. Now our change in temperature, we're going negative 40 to 0. That's a change of positive 40 degrees Celsius. All right, and let's set up for our melting. All right, so the mass of our sample, 100 grams, and our latent heat of fusion is 334 joules per gram. All right, so take a second and calculate that. Okay, so the energy requirements are listed here. It takes 8,200 joules of energy to increase that temperature of ice 40 degrees. To melt that same amount of water, we're just overcoming intermolecular forces. It requires 33,400 joules. So quite a bit of difference there. It takes more energy to overcome the intermolecular forces than just to speed up the particles. All right, let's continue with this and see what it takes to get that total amount of water up to the 140 degrees Celsius. Okay, taking a look at our calculated values for the other changes of state and increases in temperature. All 5 of the heats that we listed are on here. And one thing I want you to notice is this right here. Okay, notice 226,500 joules. That is the amount of energy needed to change that liquid water to steam, 100 grams of it. That takes a lot of energy, okay? And that's how much energy would be released if you condense that amount of water. This is why you get a very severe burn when you get burned by steam rather than just boiling water. It's because it releases so much more energy. All right. This is why steaming vegetables is a very good cooking method. It applies a lot of heat in a very short amount of time, and it goes all around the vegetables, and it does a very, very good job. Okay. So looking at all of these, and we total them up, you're going to end up with a total of 317,944 joules. Quite a bit of energy just to heat up, melt, and vaporize some water. Okay, but notice the biggest changes. Where are the biggest changes? Well, we got a big change there, there, and there. Okay, these ones on the end, not so much because we're not changing temperature a whole lot. Okay, here we change delta T is 100 degrees. Here, delta T equals 0. So that tells you something about intermolecular forces. They're very, very difficult to overcome. It takes a lot of energy to do that. Okay? So, recap here. It requires energy to change state, and the reason for the temperature remaining constant during a change of state is because we're overcoming intermolecular forces.